PQCrypto 2020, September 2020. Welcome to the talk on QC-MDPC decoders with several shades of gray. Given to you by Nir Drucker, Shay Gueron from the University of Haifa and Amazon, and Dusan Kostic from EPFL, Switzerland. What is BIKE? BIKE stands for bit flipping key encapsulation. It is a QC-MDPC code-based key encapsulation mechanism, KEM. BIKE is one of the submissions to the NIST standardization project for post-quantum crypto. BIKE has been recently promoted to round 3 of this project as an alternative candidate.
We start with explaining the timeline and describe the progress on MDPC decoders and on BIKE in general. Round 1 of the NIST PQCrypto standardization project collected submissions in November 2017. BIKE Round 1 submission proposed a CPA secure KM version where the intention was to use ephemeral keys. The decoding procedure of BIKE and basically all other MDPC decoders may fail to decode. The decoding failure rate is here called the DFR. For a CPA KEM, the DFR is mainly a matter of practicality. How often would an exchange see a failure and would need to repeat the process? However, the story is very different with the CCA secure KEM. Here, the DFR needs to be sufficiently low in order to satisfy the CCA requirement. For example, 2 to the minus 128 for level 1 security. Now this is a much higher challenge to achieve. In December 2018, Sandrier and Vasser introduced the extrapolation method. Their paper explored the step-by-step and the parallel decoders. In March 2019, BIKE Round 2 specification was released, which introduces another decoder called Backflip. BIKE Round 2 specification claimed CCA security due to first the Backflip decoder, which was evaluated to have a DFR of 2 to the minus 128 by using the extrapolation method, and second by adding the Fujisaki-Okamoto transformation to the encapsulation procedure. However, there are problems with this. The SV18 and BIKE specification did not describe the extrapolation method in a reproducible way. The second problem is that the Backflip decoder is not defined to run in a constant number of steps. It obviously did not have a constant time implementation either, which is not an easy task to achieve, certainly not with competitive performance. This is significant because adding a cap to the number of iterations in a decoder changes the DFR, and the DFR is the main property of this MDPC decoder. This means that the cap needs to be somehow factored into the DFR analysis in some way, implicitly or explicitly. Implicitly, the reference code had a cap of 100 iterations, but the choice of this number was not explained and was not mentioned in the specification document either. Now, using up to 100 iterations is not constant time, while using exactly 100 iterations is impractical. The parameters defined in the BIKE Round 2 specification do not give a sufficiently low DFR, even if we ignore the other issues mentioned above. Also, it was not clear how the Fujisaki-Okamoto transformation, as applied to BIKE Round 2 encapsulation and decapsulation procedures, achieves the desired CCA property through the proof provided in the HHK paper as claimed in the specification document. In general, for a code-based CCA secure KEM, we need a decoder that achieves a sufficiently low DFR. It has to be defined with a constant number of steps, or in our context, a constant number of iterations. And it also has to have a constant time software implementation. The performance of the constant time implementation is one of the ingredients in assessing the efficiency of the decoder. And we note that the performance of a non-constant time implementation is not a very meaningful performance metric. Now, in November 2019, we, Drucker, Gueron and Kostic, published a paper on ePrint that is also published in PQCrypto 2020, and in this paper we describe in a reproducible way two methods to perform the extrapolation. We show that the DFR depends on the number of iterations. We define a decoder called Backflip Plus that runs in constant time or with a fixed number of iterations, and study a minimal number of iterations and the block size that would yield a small DFR. This decoder can be potentially part of a CCA secure KEM. More specifically, we found that Backflip Plus with 10 iterations or 11 iterations is a practical choice that offers a nice balance between performance, DFR and bandwidth. Now the remaining question is how efficient it is compared to the other decoder, namely the black-gray decoder. To this end, we built and compared constant time implementations of the Backflip Plus and the black-gray decoders. And what we found is that Backflip Plus with the parameters of byte round 2 specification does not provide CCA security because the DFR is not sufficiently small, at least not with the estimates based on the extrapolations detailed in that paper. Based on all the provided studies, we recommended using the black-gray decoder as a more efficient alternative to Backflip Plus. And moreover, we implemented a constant time version of Bike with the black-gray decoder as an additional software implementation package for Bike. The paper QC-MDPC decoders with several shades of gray by Drucker, Gueron and Kostic that we discuss in this PQCrypto 2020 presentation was posted on ePrint already in December 2019. In this paper, we propose and study several variants of the black and gray decoders. In addition to the black-gray decoder, which was already established as a more efficient choice than Backflip Plus, we propose three new variants: the black decoder, black-gray flip decoder, and the black-gray black decoder. And we evaluate these decoders according to the extrapolation methods described in our earlier paper. The goal was to find the balance between the number of iterations and the block size that yields a decoder with a sufficiently small target DFR and a good performance. As a result of the study, we recommend using the black-gray flip decoder as an efficient constant time decoder that can be parameterized to achieve an estimated DFR of 2 to the minus 128 for level 1 security. Our methodology is generic, it is based on the extrapolation methods and can be applied to any decoder. Currently, the black-gray flip decoder seems to offer the best trade-off between the block size and the number of iterations for the given target DFR. Later on December 9th, 2019, Sandrier and Vasseur published on ePrint a paper, which was also accepted to PQCrypto 2020 and is presented in another talk. This paper provides details on the extrapolation method used for the DFR estimation of the Backflip decoder. The authors showed how to apply their extrapolation method to Backflip Plus, which was defined in our previous paper. They reconfirmed our findings that either the block size in byte round 2 specification is too small for having the required DFR, or the performance with a sufficiently large block size and the Backflip decoder is too impractical. And finally, to give a short update on the progress with Bike in spheres other than the decoder, the round 2 submission proposed three variants of Bike that we called Bike 1, Bike 2 and Bike 3. Towards the round 3 decision stage, NIST suggested that teams are encouraged to reduce the number of variants in their submissions. Until that point, Bike 1 was the recommended candidate, or at least the recommendation of the authors of this paper. The reason was that at that time, Bike 2 key generation was very slow due to the polynomial inversion. In this way, although Bike 2 has only half the bandwidth requirement compared to Bike 1, it seemed that byte 1 was still the favorite option. In December 2019, we, Drucker, Gueron and Kostic, proposed a fast method to perform the polynomial inversion in byte. And with this, we made the key generation of byte 2 finally practical. Now, the fast inversion, together with byte 2's much smaller bandwidth compared to byte 1, made byte 2 our recommended variant. However, there was still one part missing, and on April 30, together with Persichetti, we provided a proof for the CCA claim of byte 2. This required us to modify the scheme's flow in order to enjoy the proof of the HHK paper. Fortunately, our modified flows turned out to be even more efficient than the previously suggested ones. And finally, on May 20th, the byte team published its latest round 3 specification. The spec followed our recommendations for using the BGF decoder, for using the revised Fujisaki-Okamoto transformation of byte 2, and finally for choosing byte 2 as the favorite option of byte. For the CCA secure versions of byte, we need a decoder with very low DFR. For example, if we target 128 bits of security for the whole scheme, we require that the DFR of at most 2 to the minus 128. Now, all the parameters in the scheme are fixed except the block size R, which we are allowed to vary up to some degree. Increasing the block size decreases the DFR. However, it also makes the scheme slower and decreases the communication bandwidth. Therefore, our goal is to find an optimal choice for R, for which the decoder still achieves the target DFR. So far, we only know how to derive DFR heuristically. Namely, we choose the parameters of the scheme and run many encode-decode experiments and compute the proportion of failures that happen. Obviously now, if we experiment with a value of R such that the DFR is indeed 2 to the minus 128, we would not be able to experimentally confirm the DFR, since we would never see a failure. Therefore, we use the extrapolation method. We run many experiments for a set of sufficiently small values of R for which we can actually observe decoding failures, and this allows us to estimate the DFR for these R values. Then we use the collected data points to generate some extrapolation and determine the minimal value of R that achieves the required DFR. When we applied our method to byte decoders, we noticed that the R values that we get are significantly larger than the ones specified in the byte round 2 documentation. For example, in round 2 spec, byte CCA at security level 1 defines R equals to 11779, while we get R equals to 12,539. Now, this difference can be explained by two facts. First, we estimate the DFR for decoders with a small, reasonable number of iterations to make them practical, while previously the decoders were allowed to run up to 100 iterations. And secondly, we now do the extrapolation based on a large set of R values. Previously, it was done based on 2 data points only, and using fewer points makes the method more sensitive to inaccuracies and requires more experiments to get robust results. In this figure, we show an example of the DFR extrapolation for the black-gray decoder at security level 1. The extrapolation method is based on the assumption that the evolution of the DFR in terms of the block size R is a concave function. And not only that, but the assumption is that the function is at first quadratic and then after some point a linear function. Now, since we don't know exactly when this switch between quadratic and linear happens, we choose to be on the conservative side and compute the extrapolation as a linear function as shown in the left pane of the figure. Here we can also clearly see the effect of the number of iterations that the decoder is allowed to perform. You can see that, for example, if the decoder runs 4 iterations instead of 3, the estimated DFRs are significantly smaller. Now, to design a decoder that achieves the required DFR, that is securely implemented and also fast, we need to take into account several factors. First of all, the DFR can be lowered either by increasing the block size or by performing more iterations in the decoder. On the other hand, both of these have an impact on the performance, and moreover, increasing the block size has an impact on the required bandwidth for the protocol. So to find the best trade-off, we run many experiments for different values of these parameters, and finally we choose the most appealing option. In this table, we show the DFR results for the original black-gray decoder and for the 3 new decoders that we proposed in the paper. The one called black-gray flip or BGF decoder has shown the best properties out of all 4. For example, the BGF decoder, defined with 6 iterations, can achieve the target DFR with the block size of 12,277, while the old BG decoder with 4 iterations achieves the same DFR with a slightly larger block size. But BGF, defined with 6 iterations, executes 8 so-called steps, while BG executes 12 steps when defined with 4 iterations. Now, since the steps are identical in terms of performance, we conclude that by using BGF instead of BG, we can gain 50% performance improvement and also a small improvement in the required bandwidth. The second part of our paper deals with optimization of Bike's additional implementation. The most notable change that we introduced was in the decoding function. Previously, the implementation was guarded from side-channel attacks with the mock bits technique. However, this was not sufficiently secure because it could still leak some information about the secret key. Now, in this paper, we show how to implement decoding in constant time and constant memory access by employing bit slicing technique proposed by Gueron et al. In 2016. With this and some other optimizations, we managed to have the implementation of Bike, which is both secure and faster than what we had before. For example, for security level 1, the implementation with the AVX512 instruction set is about 50% faster both in the key generation phase and the decapsulation phase of the protocol. And finally, where is Bike now? Well, at the end of round 2 of the NIST project, Bike was promoted to the next round as an alternative candidate. Now, in terms of security, Bike is what we call CCA ready, meaning that it is CCA secure given that we have a decoder with sufficiently and provably low DFR. Now, based on the extrapolation method, the new BGF decoder that we proposed has lower estimated DFR than the other decoders, while at the same time being faster. And therefore, in round 3, Bike is defined with this BGF decoder. And finally, with the fast polynomial inversion used in the key generation phase in Bike 2, we showed that its performance is competitive. Since Bike 2 needs only half the bandwidth of Bike 1, it was chosen as the favorite option of Bike and the only one that is actually defined in the round 3 specification. Thank you for your attention, and the references that were mentioned in the presentation will appear in the following slide.